Mr. Charu, in this lesson we are going to be taking a look at 4 examples of integrating exponential functions with the base a. We're going to start off with a derivation or developing this rule for us that we have here. The indefinite integral of a to the u du is equal to 1 over natural log of a times a to the u plus c. We're going to then work through 4 examples. Now, through the sort of derivation of this rule, you're going to see that if we don't remember this rule, integrating exponential functions with base a can be a little bit cumbersome and go a lot quicker, of course, if we have this memorized. But why do we want to focus on the derivation of this rule? Well, that's because maybe on a test coming up later in the year, you're going to be asked to do one of these problems and you haven't used this rule, in a while. And of course, there's a lot of memorization in calculus, especially if your teacher isn't letting you use these rules as a reference, sort of like a cheat sheet, if you will. Certainly they don't let you have one on the AP exam. So, well, we do understand by now, hopefully, how to integrate natural exponential functions. The indefinite integral of e to the u du is equal to e to the u plus c. Or you might notice this e to the u du pattern as the indefinite integral of e to the u times u prime dx is equal to e to the u plus c. When I do my u substitutions, I generally have so far been trying to get, in my examples, my problems to exactly match this rule. But, if you happen to notice that you have the derivative of the exponent in your integral problem here, then you can go straight to e to the u plus c. Now, okay, well, if you look at these rules, they're not that much different. We have the indefinite integral of a to the u du, and we see that it's sort of the same pattern. It's that base raised to that exponent plus c. It's that base raised to that exponent plus c, but when you have a base a, you have this coefficient, if you will, of 1 over the natural log of a. We're going to let a be a positive real number, not equal to 1. And again, we have that same alternative form of the pattern of the integral here, the indefinite integral of a to the u times u prime dx. And so again, if you notice, you have the derivative of that exponent in that integral, or you can make that happen, then you can, of course, go to your answer, if you will, more easily. But if you look over here, we remember our derivative rules. The derivative with respect to x of e to the u is e to the u prime, and that compared to the derivative rule for exponential functions base a, the derivative with respect to x of a to the u equals the natural log of a times a to the u prime. So again, these rules are very similar as well when your base is not just base e, but base a. See, but with this rule that you're going to be memorizing, you have a multiplication of natural log of a, and with this integration rule, you sort of basically have a division of the natural log of a, or you're multiplying by 1 over natural log of a. So maybe, later on in the course, you're trying to apply these rules and you forget, oh man, was that 1 over natural log of a, or was that just natural log of a? So let's get this board cleared out and actually derive this rule in case we forget that. We need to sort of figure it out on our own. Alright, we have our indefinite integral of a to the x dx. And looking at this in the form of, or the idea of, we've never integrated anything other than the natural exponential function, let's just argue that we don't know the rule for this. So if I don't know the rule for integrating exponential functions base a, then I need to get it into base e and use a rule that we do know. The indefinite integral of e to the u is e to the u plus c. So we're going to come out to the side and we're going to let y equal a to the x. We're going to take the natural log of both sides, much like we did when we were looking at finding derivatives of exponential functions, not base e, or not natural exponential functions. Make both sides of this equation an exponent of e. Now on the left side, we're going to let that base e and that log base e, or that natural log, cancel out, and we get y is equal to e to the natural log of a to the x. And that will allow me to rewrite this into an integration problem with a base e as opposed to a base a. Okay, well now again we know that the indefinite integral of e to the u du is equal to e to the u plus c. So I know that integration rule, and so we just got done doing a bunch of videos, problems about those, and we did u substitution. So we're going to take this out on the side and say we're going to let u equal the natural log of a to the x. To be, I want to find the derivative of that, so I'm going to use the power rule for logarithms and move that variable out front, of that power out front, and that is going to be u is equal to x times the natural log of a. And just for sort of familiar, getting this in a more familiar setting, the natural log of a, I understand that that's a variable, but that's our constant variable. X is our sort of variable. So I'm going to turn this around so our constant is out front and write this as u is equal to the natural log of a times x. I'm going to wrap that natural log of a in parentheses just to make sure you don't think that the x is inside the natural log function. And so now the derivative of u, or du, is equal to, well, this is like a constant, of course, times x. Like if I say, what's the derivative of 2x, you're going to say 2. You're going to keep that constant there. So this is du is equal to the natural log of a dx. Okay, well over here, if I'm trying to get this, I'm not doing, and I'm not using the sort of pattern recognition, if you will. I'm just trying to do this u substitution to get this problem to exactly match that rule, the indefinite integral of e to the u du. So I can say it's e to the u plus c. Then I've got a substitution for my u, get rid of that reference to x, and dx, well this says natural log of a dx, so we're going to divide both sides by the natural log of a. Okay, so now I can rewrite this as, let's see, dx is 1 over natural log of a, which is again a constant, so we have 1 over the natural log of a times the indefinite integral of e to the, well, u, we let be the natural log of a to the x du. Okay, awesome. So now I've got I have my problem exactly matching an integration rule, and so now we can say 1, not L, 1 over the natural log of a times the indefinite integral of e to the u du is e to the u plus c. Okay. Well, I'm not really done yet, right? Because my problem's written, but I have a reference of u in here, and of course my original problem did not have x's. So we're going to take another step and write this as 1 over the natural log of a times e to the u. Well, what was u again? U was a natural log of a to the x plus c. And now, if I let my, I didn't want to do it up here because I was trying to get my integral into base e, but now if I let my base e and my log base e, or my natural log, if I let those cancel out, I get a final answer of 1 over the natural log of a. Okay, now letting that base e and that natural log, or log base e cancel out, I have times a to the x plus c, which is the rule that I had on my green board, which I'll put back up as we do our problems to remind you of the integration rule. The rule that says the indefinite integral of a to the x dx is equal to 1 over natural log of a times a to the x plus c. So now we can derive our rule if we forget it, which is clearly a little cumbersome, but we can do it in case we forget sort of that rule and go, oh man, okay, well, is that a coefficient of natural log of a like it was with the derivative rule, or is it 1 over natural log of a? First example, coming right up. Let's find the indefinite integral of 7 to the negative x dx. And this, of course, will be the simplest of the examples, and we'll get into more difficult ones as we go through the video. Okay, now, using that u substitution to exactly get our problem to match this integration rule here, as opposed to our pattern, which is an alternative and certainly sometimes quicker if you recognize it, we're going to let u equal, let's see, because we have, the indefinite integral of a to the x dx, or the indefinite integral of a to the u. See, our variable isn't just some little basic x, it's almost as basic, but it is a negative x. So we're going to do a u substitution here, and we're going to let u equal negative x, which makes du equal to negative 1 times dx, which, I'm sure most of us are just going to write negative dx. And go, okay, well there's a dx there, but there's not just a dx here. We need to divide both sides by negative 1. So we get negative du is equal to dx, and now we're ready to remove all references of x in this problem. And we do get the indefinite integral of, let's see here, we're going to let the u equal negative x, and dx is equal to negative, so we'll pull that negative 1 out front, du. And referencing our rule, we have, well, that's supposed to be equal to 1 over natural log of a times a to the u plus c. So that's going to be equal to, now I have a negative out front, so negative 1, you can write that in parentheses if you want, but, well, I'll do that for a second, it's kind of pointless. But negative 1 times 1 over natural log of a. Well, a is our base, right? A is the base, or base is 7, so it's 1 over natural log of 7 times a to the u. Well, basically kind of like what we started with in the first place, so a to the u, or 7 to the u, plus c. Now, normally I would just write the negative 1, have like negative 1 times 1 over natural log of 7 times 7 to the u prime, because if you write it like this with the parentheses, you have to distribute the negative 1, and then we have negative 1, I'm going to get rid of the u now here as well, over natural log of 7 times 7 to the u, which is negative x, and then negative 1 times this constant makes it a negative constant, and if you really wanted to be picky, you'd have to put like a little subscript to show that it's a different constant of integration. And of course you can write this as, well, that's perfectly fine. You can also write negative 7 on top. Now, as far as the pattern recognition goes, and that's the final answer of course, if we didn't, and I do generally do my u substitutions like this to get my problem to exactly match the rule, but I could look at this as using this alternative form here, which I don't at this point in calculus yet like to use it very much, because I have some students, you know, that will read my books, of course, which is always a great idea to read the textbook, but they've been trying to, with some problems, get their problem to fall into this pattern and do that pattern recognition, and kind of messing up the problem sometimes with the ones that are a bit more difficult. So far, and actually I'm more comfortable with myself making this u substitution, using that to rewrite our problem to exactly match the rule, but this isn't too terribly difficult, so I could say, well, let's see, if I could get that a to the u times u prime pattern to show up, we have the indefinite integral of 7 to the negative x. My u is negative x, so u prime would be negative 1, so if it was just 7 to the negative x times negative 1 dx, if I could get that negative 1 to be there, the derivative of the exponent, then I would, match this pattern and I'd be able to write the answer. Well, if I introduce a negative 1 out here, I would be changing the value of my problem, right? So I'd have to multiply by a negative 1 out here to balance that out, and the negative 1 times negative 1 is equal to 1. Or you could say, well, if I multiplied by 1 in here, negative 1 in here, then I would have to divide by negative 1 out there, kind of academic with the 1, right? Because multiplying by dividing by 1, that's an identity for multiplication and division, kind of doesn't really appear to do anything, but if that was a negative 2, then you would definitely want to 1 over negative 2 out front. And then that follows right into this pattern, and we have indefinite integral, a to the u, u prime dx, indefinite integral, a to the u times u prime dx is, well, had to move that division of negative 1 out front, or that, result of having a multiplication of negative 1 out front, over natural log of 7 times 7 to the negative x plus c, or constant of integration. So, kind of over-explained the first one there a little bit. It's about as basic as these are going to get, unless that's just an x. So let's step up the difficulty a little bit more. Bam! Second example. Product rule, right? Two things being multiplied together. Oh, wait a minute. There's no product rule with integration. So, must be, well, okay, let's see here. We got a base that is a constant. We have an exponent which has got a variable in it, so maybe we're going to be talking about integration of exponential functions base A. So, we've got, let's see here, a to the u, something constant, variable exponent. Constant, variable exponent. So let's try and let u, let's put this in yellow, let's let u equal negative x squared. Well then du is going to be equal to negative 2x dx. Oh, okay, so this is actually already starting to fall out pretty nicely here. We have an x dx and x dx, except my u substitution here has a coefficient of negative 2, where this coefficient is positive 1, so we'll divide both sides by negative 2 and get negative 1/2 du is equal to x dx. Oh, okay, so this is an integration problem which we're going to be allowed to, or be able to use our rule here for exponential functions of base A. So we have the indefinite integral, we have that 3 to the u, and we've got our x dx is equal to negative 1/2 du, so negative 1/2, move that out front, and our du. Now again, focusing on, recognizing this pattern or making this pattern show up, we have a variable exponent again, and the derivative of that u would be negative 2x. So I could put a negative 2x here and have my u prime dx, and then of course, but if I'm going to put a negative 2 in front of that x, I would have to do what up front? Balance it out with a division of negative 2, which is actually what the u substitution process is doing for us. And so now this is going to be equal to negative 1/2 times the 1 over the natural log of a, our base, so the natural log of 3, times a to the u, or 3 to the u, plus c. And again, that u is what? Negative x squared, so we have negative 1 over 2 times the natural log of 3 times, or you can have it up front, times 3 to the negative x squared plus c, and that is the end of our second example. Let's move on to the third, shall we? Find the indefinite integral of 5 to the 3x power over 2 plus 5 to the 3x power dx. Well, we're talking about exponential functions, base A, and we've been doing some u substitutions with the exponent. So I have a constant base and a variable exponent, so must be an exponential function base A, right? So if that's the case, we're going to let u equal 3 to the x, and then du is going to be equal to 3 dx, and I'm going to get this all, substituted in and get it into this pattern of a to the, the indefinite integral of a to the u du, so I can write the final answer. Well, I've got a u substitution there. I can divide both sides by 3 and get 1/3 du is equal to dx, but, excuse me, what am I going to do about that 2 in the denominator? That's a problem. I mean, I could write it as 5 to the u over 2 plus 5 to the u dx, but again, there's no integration rule for the quotient rule. I mean, there's a derivative rule for quotients, but not integration. Well, at least not the pattern of this. So, well, let's try something else with our u substitution. We had some kind of pattern in there somewhere, right, about the indefinite integral of u prime over u. So let's just let the whole denominator equal u and see what happens. So u is equal to 2 plus 5 to the 3x, and that means that du is going to be equal to, well, the derivative of a constant is equal to 0, and now we have to remember the derivative of exponential functions base A. Well, the derivative of e to the u is what? E to the u prime, but this is a to the u. So that's going to be, Well, let's see, if we remember our integration or derivative rule for exponential functions base a, I don't have to convert this into base e and go through all that work. So it's going to be equal to the natural log of a, our base, which is 5, times a to the u, or 5 to the 3x, times u prime, which is 3. Okay, so then I'm cleaning this up a little bit. We have dx, and then we have du is equal to 3 times the natural log of 5 times 5, 3 to the x, dx. Okay, so I've got a u substitution for the entire denominator. I've got 5 to the 3x dx, 5 to the 3 dx, but that's it, right? So I need to get this constant to get it to exactly match, and do the u substitution, get it to exactly match. Well, actually I'm pointing at that, but that's not really the rule we're going to use. I'm going to pull this out front. Oh, I forgot my u. We get 1 over, chalk down, 1 over 3 to the natural log of 5 du is equal to 5 to the 3x power dx. Alright, now I got a lot of u substitutions set up here. Let's see how I can rewrite this. This is going to become, and I think this is going to be in our way. Let's see if I can scoot this down without it falling off. Alright, stay. That is going to become the indefinite integral of 5 to the 3x dx, 5 to the 3x dx is du, and remember this is all constant, so that 1 over 3 times the natural log of 5 is going to be our coefficient out front, and we have du as our numerator, or I can have 1 over and then my du off to the side, which, let's go ahead and do that. And our entire denominator is equal to u. Oh, so this problem started off, you know, everything's been integration of exponential functions base a, but I really end up with a situation where I have 1 over u du, or u prime, or du over u. So this is actually the integration rule for the natural log function. So this is going to become 1 over 3 times the natural log of 5 times the natural log of u plus c. And our u was 2 plus 5 to the 3x power. And I don't need the absolute value symbol because this expression is never going to be negative. And let me just make sure I didn't make any mistake in here. Looks good. Now, that might not be the way that you see this problem in your textbook. So let's get this out of the way and show a few steps that we can do to simplify. Actually, I would probably just leave my final answer like this, but if you're trying to check your answers in the back of the book, you might not see that answer. So let's see what that would look like. So, just plopping that natural log function on top of the fraction of natural log of 2 plus 5 to the 3x. That, when you multiply, what exponential rule or properties of exponents allowed you to take the exponents and multiply them together? Well, you did that when you had a base raised to 2 exponents, basically, and you would kind of recognize those as being stacked. So 5 to the 3rd power raised to the x power, 1 base 2 stacked exponents, and that would be the phone. Thank you. Sorry for the interruption. So that stacked exponent thing there, we have 5 to the 3rd to the x power, and of course 5 to the 3rd power is 125. So there's just a way that the final simplified answer, if you want to call it that, in a text or some kind of solutions guide may not look exactly like what you have, but you didn't make a mistake. One last example is going to be a definite integral involving a little bit of basic trig functions. Here we go, last example. Find the area bound between the equations. Y is equal to 5 to the x, let's try that again. Y is equal to 5 to the sine x power times 2 times cosine of x. Also bound by the line y is equal to 0, this horizontal line, which happens to be the x-axis. X is equal to 0, which is the y-axis, and x is equal to pi over 2. So basically our boundaries are x is equal to pi over 2, x is equal to 1, y is equal to 0, and then of course our function right there. Now, while definite integrals can be negative, area cannot. So you might want to check out that graph and make sure that when you set up your definite integration, it is going to come out to be a positive answer where you take the function that is on top. Basically, we're going to be doing, this function of 5 to the sine x power times 2 cosine x and subtracting it with the other function, which is equal to 0. But when we subtract by 0, really nothing happens. So it's not going to seem like I'm doing a subtraction between two functions, but we are. So also, finding our x-intercept here, because if the function goes below the x-axis, our area is going to be negative. If we keep up, if we keep this pattern of our trig function, if you will, subtracted by 0, it would come out to be a negative area. But when you put this into your calculator and check the graph, the 0 is pi over 2. So we don't have any worries about an area portion coming out to be negative. That's actually coming up later on in our textbook. So we are doing the definite integral from 0 to pi over 2 of 5 to the sine x power times 2 cosine x, and don't forget the dx when you set up your definite integration, or any integration expression for that matter. So that looks like kind of like a 6. Okay, so that clearly is fairly complicated looking. Let's go ahead and take this out of the way so I have some more room to write. Probably should have erased my problem. Sorry about that. So we're going to let's see here. We do, again, have a constant to a variable exponent. So let's see if we follow that pattern of the integral of a to the u du. So we're going to let u equal sine x. Okay, so that means that du, the derivative of sine is of course cosine dx. Okay, but we have a 2 here where I don't have a 2 here, because with my u substitution I want to make it exactly match the rule and eliminate all references to x. So we're going to have 2 du is equal to 2 cosine of x dx. I could have also just moved the 2 out front there and not had to worry about that. Now if I do my u substitution, with my definite integration, with my definite integrals, I like to just remove all references to x and not have to go back into the original variable, because our answer is going to be a number, not another expression or function. So leaving this lower and upper limit of 0 and pi over 2, those are in terms of x, not in terms of u. So I got to do that as well. My new lower limit, or actually let's do upper and lower, my new upper limit is going to be, well, u is sine of x. So my new upper limit in terms of u is going to be the sine of pi over 2, which of course I'm hoping we know our unit circle is equal to 1, and our new lower limit is equal to the sine of 0, which is equal to 0. I got some new chalk and it's too hard. I need to go buy some softer stuff. So sorry about the squeak in there so much. Actually, let's just switch to yellow so it'll be easier. Alright, writing and talking at the same time doesn't always work, so let's try this again. All this u substitution stuff is set up. Let's get this written in terms of u and eliminate all references to x. Our lower limit is 0. Our upper limit is 1. Our 5 to the sine is going to become 5 to the u. Our 2 cosine x dx is, again, that 2. Going to pull it out front. And here's my du. And I exactly match our integration rule for exponential functions base a. that's going to become 2 times, okay, so here our rule said that we had 1 over the natural log of a, which is 5, times a to the u, but this time I'm actually going to write the 5. 5 to the u with our upper limit of 1 and lower limit of 0. And that is going to become 2 times 1 over the natural log of 5 times 5 to the first minus 1 over the natural log of 5 times 5 to the 0 power. And that is going to become, well, anything to the 0 power is 1, so we just have 2 times 1 over, or actually let's just put that 5 on top, 5 over the natural log of 5 minus, well, 1 over the natural log of, that looks like an exponent, of 5 again. And you could pull the net 1 over natural log of 5 out if you want and write that as 2 over the natural log of 5 times, now we have 5 minus 1 after you pull that out, which of course is going to be equal to 4. And 4 times 2 is equal to 8, just, of course on top. 8 over the natural log of 5. And that is the end of my last example, second take. So, I'm Mr. True. Go do your homework.